Let's get started because we have lots of stuff to talk about today. So hello to all the people online. Remind me to pass out the roll sheet, right? So because I will surely forget. So in a few minutes, remind me to pass that out. So next time is the test, right? The answer, the solutions, the answer key, but actually the solutions to the sample test are posted already along with the sample test on the Blackboard page, right? So I posted that yesterday and sent an email about that. Also on the Blackboard page is, if you go to class notes and videos, there is a video of a review of highlights of that review, where I'm sort of discussing the solutions to that sample test. And but this only covers certain problems, mostly the trigonometry part of the sample test, and then I think about function direction increasing and decreasing, and then also average rate of change. So that's through problem 15 or something like that on the sample test. And we're going to look at other problems from the sample test though right now. Okay, so but can't do all of that in class because that's too much. So you can watch that tape if you need to for reviewing other parts of the sample test. So if you haven't started studying, right now's the time. Okay, so you need to start studying immediately, right? Because there's a lot of material for the test because it includes the trig. So don't forget about your survival card to make out your survival card. And I want to especially caution you, right? You need to know the trig ratios for the special angles, right? So you need to know sine, cosine, tangent, etc. for the special angles, 0, 30, 45, 60, 90, right? Okay. Yeah, it stops at inverses, I think. Yeah, composition and inverses, right, is where it quits. So this homework that is due tonight, although it's due tonight on trigonometric graphs, is not covered on the test. There's no trigonometric graphs on the test. So now remember, for the trigonometric graphs, you're going to be asked to compute things like amplitude and period, right, and phase shift, and then perhaps construct graphs. But remember, you can use graphing tools to construct the graphs, right? So at the top of that homework, as I pointed out a couple of times, right, there's a link to Desmos where you can graph, or you can use your graphing calculator to construct the graphs for the homework, right? And the same thing on more trigonometric graphs, since we didn't really discuss the graphs of tangent and cotangent and secant and cosecant that closely, right? So this is a very short homework, but be sure to use either your graphing calculator or the Desmos link, right, to construct the graphs that you're asked to for this homework. Okay. All right. So we're going to look at the last part of the sample test right now. Do y'all have any questions though for me? So remember, it's going to be A through M, right, coming at 10, and then the rest of you guys N through Z will come at about 11:15 approximately, right? That's when around that time is when we'll start the second half. Yeah. Huh? It's Wednesday. Okay, right. So I'm always disconcerted when I get that question. And when is the exam? Because we've talked about it several times, right? Okay, so you might put away your phone and be paying closer attention, and then maybe you would know when the exam is. All right. Let me see if I can find here. Here's a copy of the sample test, right? And so we'll just go over some of these problems, starting with problem number 21. Okay. So I'm going to lower the screen here for you guys online so that I can hopefully write here without too much difficulty. Hopefully we won't have same issues that we had last week there with writing. Let me see if I can picking this up a little bit. Yeah. that's fairly thick, so that should do. Okay, all right. So this question is a little bit unusual because you're not used to evaluating function notation looking at a graph that much, right? Although we have done it in class. So sometimes students get a little bit confused by this question, but it's really actually easy. Okay, you're just going to make it difficult because you're not used to doing it this way. So for instance, if you're asked to compute, so here's the graphs of two functions, but we're not given the formulas, right? So you want to compute f of 0 and also g of 0, just reading the graph. So make sure you pick out the right graph. This is the graph of f. So f of 0, right, is just, you're going to find 0 on the x-axis and then look at what f of 0 is, which looks to be, counting off here, what, 3, right? Okay. You have to kind of read here a little bit carefully. I think that's 1, 2, 3. So so the answer there is just, that's pretty easy, right? It's just 3. No, that's not thick enough. So let's try thicken that up a bit. See if that's any better. Okay. All right. And then g of 0 the same way, right? So find 0 on the x-axis, right? So it looks like g of 0 is down here at -1, -2, -3, -4, right? So g of 0 there is -4. Well, that's pretty straightforward, right? So that's probably pretty easy to do. But now here, this is really a composition, right? It's just not expressed as a composition, but this is what we're really doing. We're composing these two functions, g and f, right, by computing g of f of 0. But so you work inside out, right? You're going to compute f of 0 first and then apply g to that result. But you already know what f of 0 is because, right, we just calculated in the prior part. So this is really g of 3 because f of 0 is 3. And now you have to compute g of 3. Hopefully you can read that from the graph of g, right? So there's 3 on the x-axis. This is the graph of g, right? It's the straight line. So it looks like g of 3 is equal to 2, right? So this just turns out to be 2. What about f plus g of 0? Remember, that means that's the sum of these two functions, but that means f of 0 plus g of 0. Remember, f plus g is a new function formed by adding the two existing functions together, right? But the way you calculate f plus g of any input is just f of that input plus that input. So even though you don't know what the formulas for f and g are, and you certainly don't know what the graph of f plus g looks like, right? You can still calculate f plus g of 0. And well, since we've already computed f of 0 and g of 0, right, this is easy to calculate, right? This is just going to be 3 minus 4, right? F of 0 is 3 and g of 0 is -4. So you get, looks like -1 there, right? So don't get confused by that. Don't get confused by, by this evaluation just because you only have the graphs. What about f of 1? Well, from the graph, that looks like 2, right? There's 1 on the x-axis, so it looks like f of 1 is 2. And g of 1, it looks like -2, right? Because there's the graph of g. So at 1, we go down to -2. And now we have another composition, but this one really is expressed as composition, right? This is g compose f of 1. But remember, that means sort of the same thing that we did in part B, right? The g compose f of 1 means g of f of 1. But what's f of 1? We already know, right? Because we computed it in the prior part. So f of 1 is 2. So what we're really calculating here is g of 2. What's g of 2 look like there on that graph? Is it, Emil? So the g is the straight line. So find the straight line. Go to 2 on the x-axis. So what's g of 2? All right, guys, we're just going over this. Yeah, it seems like 0. That's what it is. Right, you're right. Okay, it is 0. And now f minus g of 1. See, that's so easy now. That's f of 1 minus g of 1. But again, we know what both of these things are, right? So f of 1 is 2 minus g of 1 is -2. So make sure you write down both minus signs. this minus is part of the function definition, right? This minus is part of the fact that g of 1 is -2, right? So you really have there 2 plus 2, which is 4. Okay. So see, those are almost gimme points, right? If you have a problem like this on the test, but students miss this problem frequently when it really just easy points, right? Just because they're expecting formulas for F and G, not graphs for F and G. All right, now of course we did this a lot last time, so you're pretty familiar with this type of problem from the lecture last time. But again, there's not much of this in the homework, so if any. So problems 22 and 23 you really should look at before the test in case you get a problem like this on the test. So so we want to find two functions f and g, right? So that when we compose them, we will get h, which is sine cubed of x. Remember, sine cubed of x means sine of x to the third power. That's not the same as sine of x cubed. This means you cube x, and then you take the sine of that cube. This means take the sine of x first, and then cube that result. Okay, so these two things are actually identical. The reason that they write it like this is just laziness. Don't want to have to use parentheses. Okay, so because people were raising trig ratios to powers before they started using parentheses in math notation. Okay, so mathematicians started writing sine cubed of x, or sine squared of x, or sine to any power of x like this, so that they could distinguish it from this different expression, right? Okay, because they didn't at that time use parentheses math notation. So these two things are the same. All right, so well, now that we see it, now that we can see what sine cubed of x really means, right? It's the sine of x, and then we raise all of that to the third power. That gives us an idea, right, of what our two functions should be here. Fernando, you have any suggestions for what two functions we can use so that when we compose them, we get this result? What are the two sort of key things that are happening in this formula? Yeah, so you have what now? You have sine of x, and then you have a cube, right? So one of the functions, let's make sine of x, and the other ones will make the cubing function. So it's just a matter of picking which one you want. Okay, so you might get it backwards. Maybe this is backwards. So let's let f be sine of x, and then let's let g be x cubed, the function that cubes its input. Okay, because those are the two key operations that are happening here. Now let's check these by composing them and see if I got it right. Have to be close to correct, right? So f composed g of x, that means, as always, f of g of x, but g of x is what? X cubed, and then f of x cubed would just take the sine of that. See, we got it backwards there, right? This means you cube x first, and then you compute the sine. But we wanted to compute the sine first and the cube. So, we'll just switch them, right? Okay, we just got these out of order. So I'll put the cube here, right, and sine of x there. Now, when you compose them, see, it's going to come out different. You have f of g of x is sine of x, and f takes all of that and cubes it. So you get sine of x raised to the third power, which again, you can write as this if you don't want to write parentheses down. Okay, you're going to see this expression a lot, okay, where you're taking the sine of a number, cubing it or squaring it or raising it to some power. So remember, you can write the exponent by the sign, all right? Then you don't have to parentheses. All right, let's try. I think this is a multiple choice question. So we don't often get multiple choice questions on tests, right? So on my test anyway, not on tests in general, but in my test. So let's see what the instructions are. It says in part of this problem, a transformation of this function They don't tell us what this function is, but that looks a lot like the sine curve, right? So I think that's a transformation of sine curve. It doesn't say that. Transformation of this function shown here has been graphed. Choose the correct formula for each transformation. So you have to look at, what the graph of the transformation looks like, and then try to figure out what's happened, right? Okay, so which would be the right formula? What does it look like we've done in this part A, right? And moving from this graph to this graph, it looks like we've just what now? Yeah, it looks like we've done a vertical stretch, right? Okay, we've made the graph taller. If this really is the sine curve, then we've changed the amplitude, right? That's called changing the amplitude. And it looks like we've tripled it, right? Because this used to go up to 1, now it goes up to 3. Notice it has not been stretched horizontally, I don't think. We don't have a horizontal stretch because the intercepts are all the same, right? Notice the x-intercepts here are 1, 2, 3, 4. Oh, so this is not the sine curve. Okay, so this graph here is not the sine curve, because sine curve does not have intercepts at 1, 2, 3, and 4, right? Not that easy, correct? But anyway, here you've got the same intercepts, right? So you haven't. It doesn't look like you have shrunk this horizontally. Okay, just vertically you've amplified it, right? And so you said it right there. You multiplied by 3, so that's this one, correct? Right, we've just multiplied f by 3, right? So what's happened here? That does look like a horizontal shrink, right? Okay, because before you had your first x-intercept at 1, and then another one at 2, right? But now you've got x-intercept at looks like 1/2, and then another x-intercept at 1. So it looks like we've shrunk this by what factor? Yeah, well, you can say it either way, right? By a factor of 2 or by a factor of 1/2, right? We've shrunk that. Okay. So what's the correct formula there? Oh, we have to be careful, right? Is it this one? Yeah, I think that's right, isn't it? Okay. Because if this constant, that you're going to multiply x by a constant, right? That's what gives you a horizontal shrink. And if this constant is 2, then that means you've shrunk by a factor of 1/2, 1/2. Okay. So that's correct. All right, here they're going to ask us to perform a transformation, I think, and write down the new formula for that. So here we have this function, which is 5 times x times 2 raised to the x power. Okay. We haven't seen a lot of functions like this, where we have a base raised to a variable power, but we're going to look at functions like that shortly. This is called an exponential function because your input variable x is in the exponent here of this base. Well, no matter what the function is called, there's its graph. So you get a graph that looks like this, right? Okay, so it's kind of an interesting graph, right? It does have a local minimum here, right? Okay, this turning point is a local minimum. At first, the curve is decreasing, right? And then it starts to increase. The question here, though, is why does g, this function, not have an inverse? So this is not an invertible function. So if you had to explain that in words, what would you say? Yeah, it repeats a y value, right? Okay, and there are plenty of them that get repeated here. For instance, if you look at -2, right, that y value shows up at this point on the graph, right? Okay, and also at this point on the graph, right? So you have repeated, different points, right, on the curve with the same y, right? Can't have that in an invertible function. So it does not have an inverse, so we don't have to worry about that. Let's see what we're asked to do here, though. We want to write a formula for a function h that, so that the graph of h is exactly the same as the graph of g. It has the same shape, but we want it to be shifted to the left by 2 units and up by 5 units. Okay, so so those are some horizontal and vertical shifts. Those are easy to accomplish, right? You're just adding or subtracting constants, right, in the correct place. Adding or subtracting, not multiplying, right? When you multiply by constants, that's when you're getting stretches and shrinks. Okay, those are harder to think about, right? Okay, but the shifts where we're just shifting left or right or up and down, those are usually easier to think about, right? So how would you change the formula of G so that you accomplish these shifts, right? So I'm just going to first use the name for the function G, and then we'll fill our what we get here into the actual formula G. All right. So what do you do to move it to the left? Add 2 units to what? X, right? Okay. So you would have G of X plus 2, right, instead of just G of X. And then how do you get it shifted up? Just plus 5, right? Okay. So just at the end there, right, you just add 5. So what does that look like in the formula for G? Let's remind ourselves of the formula for G. That's 5x 2 to the x power, right? Unfortunately, I can't get those both on the screen. So 5x times 2 to the x power. So we would get 5 times, instead of x, we would have x plus 2, right? And then times 2, instead of to the x power, it would be to the x plus 2 power, right? We would plug in x plus 2 wherever we see x in the formula for G. So you're going to get something like this. And then don't forget, at the end, you're going to have to add on the 5, right? Okay. So get this kind of funky formula, right, for that new function H. So that would shift this graph up. What is supposed to go up 5 units and what, to the left 2 units, right? So get in this direction. All right, well, we're getting close to the end. I think so these things not so difficult to me. I think y'all should do good on the test, right? If you review properly. Let's do 28 first, because that has some algebra in it. So and I know a problem like this is on the test. Okay, so I'll give you a heads up for that right now. Okay, you'll have to a problem like 28, where you're given a function G, just x over 1 minus 2x. So I guess that function has an inverse. Not really asked to discover if it has an inverse or not, but we are asked to write down the formula for the inverse, right? We want to write down what's the formula for G inverse x. So I guess that means it must have an inverse. Otherwise, we couldn't write down formula for the inverse, right? So we just have a little algebraic process we have to go through, right, to discover the formula for the inverse. And you guys recall what that was. First, change the G of x to y just to make the left-hand side here easier to work with. So you can write y equals x over 1 minus 2x. And then what's the key step here? Yeah, flip x and y's, right? Because remember, that's how inverses work, right? We're reversing the x's and the y's. So you would write down x equals y over 1 minus 2y. So maybe there's something you want to write down on your survival card, right? Okay, a little reminder of how you find inverse formulas. Finding inverse graphs is a little bit different, although it's really the same process, right? Okay, to find the graph of the inverse, you're also flipping x and y coordinates, but of course you can't do that for every single point on the graph, so you need kind of a shortcut there, right? But for formulas, you're going to do it physically. You're going to flip the x and the y, and then do what? Yeah, solve for y, right? So so you turn around and solve the equation back for y. All right, so to do that, let's get rid of the fraction, right? So multiply both sides by 1 minus 2y, or you can think of it as cross multiplying also. So multiply both sides by 1 minus 2y, this denominator, so you can just cancel the denominator on the right-hand side, right? So you have y is equal to 1 minus 2y times x, and then go ahead and distribute on the left-hand side. So multiply the x through. So you get x minus 2xy equals y. And now here's the second other important step. We want to solve this equation for y. So what do we have to do with the equation to solve for y? Not yet. Okay. Move the x to the other side. That's part of the process of moving the y's to one side. Okay. So all the terms that involve y, since you want to solve for y, ultimately, all the terms that involve y, get them on one side of the equation. I like to put them on the left, but that doesn't really matter. Okay. And then all the other terms that don't involve y, put them on the right-hand side of the equation. So you're separating terms, right? So let's move. How do you want to do that? Well, since I said left, let's take the y there and this y and move it to the left. And let's take this x and move it right. Going to make the signs a little bit messy. I might have been better moving things in the other direction, but too late now. So I have minus y, and then what? Minus 2xy, right? Is equal to minus x. Yeah, I'm ending up with a lot of minus signs here, but that's okay. And now, next step. Nope. Okay, but what's important here? Factor out the y. Okay. So you have y times x minus 2x, right, is equal to, is that right? No. Minus 1, right? Okay. When I factor y from this first term, I get left with a 1 because I factored out the y. And then when I factor y from this second term, I do get left with minus 2x. So you have minus 1, minus 2x equal, and then on the right-hand side, the minus x. Now, finally, you can divide, okay? So divide both sides by minus 1, minus 2x. Minus 1, minus 2x. And so there it is. So you get y is equal to minus x over minus 1, minus 2x. Had you done this a little bit differently, the way you arrange the terms on either side of the equation, you would have probably ended up with x over 1 plus 2x, which is the same fraction. Those are really the same. So if you were doing this at home and you get x over 1 plus 2x, and I have this, they're really the same. So don't get disturbed by that. All right, so last one here, then let's scroll up. The last thing we want to do now is, there we have a function. That function is increasing from left to right. So that means that it must have an inverse, because since it's always increasing, it cannot repeat any y coordinates, right? So you know it must have an inverse, and we want to see what the graph of the inverse looks like. So, and that really means you're flipping all the coordinates, the x and y coordinates for all the points on this curve, but you cannot do that, one at a time, right? So, so you have to think about what the net effect is when you flip all the points on the curve, and what is the ultimate effect of that, as we discussed in class. Actually, we proved, right, what happens when you flip all those points. What now? It reflects around what? Yeah, it rotates it or reflects it around the line y equals x, which is this 45-degree line, right? So let's scribble in a 45-degree line. There's the line y equals x. And then let's just visualize, right, what happens when we rotate this graph. It's hard to call it a curve, right, because it's not very curvy. But when we rotate this graph around that 45-degree line, so what's going to happen here? Well, just sort of visualize it, right? Okay, I think this piece in the middle, right, that's above the 45-degree line, it's going to get rotated around, right? So it's going to come out down something like this, correct? That piece. What about this piece that's below the 45-degree line? it's going to go above, right? So it's going to get rotated up like this. And this piece, also below the 45-degree line, right? Also is going to get rotated around and above, right? So it's going to come up something like this. So well, that's a little bit not very sure-handed of me, but there's what the there's ultimately it's going to look something like this, right? So if you can get that close on the exam, then get full credit for that. Okay, well, all these problems seem very doable to me. So so I think if you prepare, then you have a good chance there of doing well. Okay, be really beneficial for all of you, of course, right? Always to make a high score on the test, but for those of you who already did really well on the first test, and another high score would really make you feel a lot more comfortable during the last month of the semester. And for those people who didn't do so well on the first test, you know, high score is going to really improve your average and also improve your confidence as well, right? So you should, so everyone should be aiming for that good grade on the test, right? So you don't get stuck in the unfortunate position of having to repeat this class, because it's an expensive class to repeat. It's a 5-hour class, right? So you're paying a lot for this. Okay. What now? To back. Oh, all right. Jakayla, what about 28 there? Did I just scroll too fast there, or were you writing down? Remember, the solutions are on the. You don't really have to copy all of this slavishly, because the solutions are posted, right? So the solutions are on the Blackboard page, right? Already, so you don't really have to recopy all of this immediately. Or do you have a question about this, what I did?
Yeah, whenever I was solving it,
Uh-huh.
you know how it's negative y and negative 2x?
Uh-huh.
And
Where?
then you,
Right here?
yeah, and then you move the negative, or you distribute the negative from the y. But I was asking, why
I
isn't
didn't
it?
distribute I didn't distribute the here. I didn't do anything with the negatives. I just factored out the y, positive
Um,
y, but I left the minus signs where they were.
okay.
So when I factor this y out, I'm left with a -1, and when I factor this y out, I'm left with a -2x. So I kept those, and then divided by what was in parentheses here, which was -1 -2x on both sides. So is that clearer now? Okay. All right. All right. So other questions there about what's going to be on the test? Let me. We're going to go back to the notes now. So because we're talking about inverses of trig functions, this is kind of good preparation for the trig part of the test, although the trig part of the test is easier than inverses of trig functions. I'll pass the roll. So last time we were talking about inverse trig functions, right? Which are going to be really important for us, in particular in helping us solve equations. And that's really how inverse trig functions, not just inverse trig functions, that's how inverse functions really help you in general, is help you solve certain equations. We're going to see that again shortly with a different type of function that also has an inverse. So remember, the way these inverse trig functions work is they're inverses, right? So with an inverse trig function, you put in a number and you get back an angle, right? In the regular trig functions, right, you put in an angle and you get back a number. For the inverse trig functions, you put in a number and you get back angle, right? In particular, you get the angle that gives you that number as the trig ratio, right? So So I think the way these functions are designed to work is pretty easy, except what's complicating about them, right? Remember, is that unfortunately, the original standard trig functions do not really have inverses, right? So we have to restrict them. We have to restrict their domain so that you get an invertible function. So remember, the inverse trig functions are really inverses of not the original trig functions, but the restricted trig functions. And the effect of that on the inverse is you get you have to be careful and know the range of your inverse trig functions. This is just something you have to memorize, okay? Because it turns out to be really crucial in problems sometimes. So for the inverse sine function, remember, you put in a number, right, and you get back an angle. But the range of that angle always has to be between minus pi over 2 and pi over 2. So please keep that in mind. You have to get an angle between minus pi over 2 and pi over 2. For the cosine function, not quite the same range. I'm sorry, for the inverse cosine function, not quite the same range. Again, it works the same. You put in a number and you get back an angle, but the angle you get back for the inverse cosine function must be between 0 and pi. Now, all of the inverse trig functions have restrictions on their range that you have to remember. But if you can remember sine and cosine, you can remember the others as well, okay? Because the others are similar to the restricted ranges for sine and cosine. So for tangent, again, you put in a number, you get back an angle. The angle you get is between minus pi over 2 and pi over 2, like the sine is. The way I suggested you remember that for tangent is, remember, tangent is sine over cosine, right? Since sine is over cosine for the tangent, sine is in the numerator. It's the range of the range of the sine, the range of the inverse sine will be the same as the range of inverse tangent. So for tangent, it's the same as sine. Cotangent, though, is the opposite, right? Cotangent is cosine. Cotangent is cosine over sine. So the range of the inverse cotangent is the same as the range of the inverse cosine, which is 0 to pi. What about secant? Secant is 1 over cosine. So the range of the inverse secant is going to be the same as the range of the inverse cosine, which is 0 to pi again. And then cosecant is 1 over sine. So the range of the inverse cosecant function, which we really don't use that much, but the range of the inverse cosecant function is the same as the range of the inverse sine, which is minus pi over 2 to pi over 2. Okay. The three that we'll use most frequently are inverse sine, inverse cosine, and inverse tangent. So you really need to remember their ranges. Okay. That is, what size angle you can get back out of inverse trig functions. All right, I'm going to give you a little bit of recall practice here then. See if I can find it. It's all of our sloppy writing from last time. Okay, so there's the recall practice in the margin. So for you guys also at home, I want you to see if you can find for me inverse sine of square root of 2 over 2. So remember, the way inverse sine works is, right, you put in a number. Here we're putting in square root of 2 over 2. You get back an angle, right? Okay, so put in a number, you get back an angle. And what do you know about that angle? So let me call that angle that we get back y. What do you know about that angle? The sine of y has to be what? It has to be this number, square root of 2 over 2, right? That's the way inverse sine function works, right? Okay, put in some number, you get back an angle. And what do you know about that angle? The sine of that angle has to be whatever this number is. So now you just have to think about it, okay? What angle gives me sine square root of 2 over 2. Give your answer in radians, though. Make sure you give your answer in radians. Okay. So it's just that easy to answer that question. This one you should have memorized for your this one you should have memorized for your test already. Okay. What is that angle? Which, yeah, in radians is what? Pi over 4, right? Okay. So we know here that y has to be pi over 4. But now, Evan, the other thing you have to check is, this is the irritating part of the inverse trig function. You have to make sure that the angle you get back is in the proper range, which has to be between 0. No, I'm sorry. For inverse sine, it has to be what? Yeah, minus pi over 2 to pi over 2. Is pi over 4 in that range? Yeah, it is, right. Okay, that's right. Easily in that range, right? Okay. So that's it. We know we've got that's it. We know we've got the right answer. All right. So now this one's a harder one. So I want you guys to try this one. Arc cosine. Arc cosine is the same as cosine inverse, right? That's the old-fashioned name for cosine inverse, right? So the way you start this is, okay, I'm going to call this y. I know y is an angle. And what do I know about the angle y? Its cosine has to be minus the square root of 2 over 2. So you've got to find an angle. Its cosine minus, it's negative now, minus the square root of 2 over 2. And make sure you get it in the proper range, which is 0 to pi. 0 to pi for inverse cosine. So you have to find an angle between 0 and pi that has that number minus square root of 2 over 2 as its cosine. So just think about it. That's why I drew a little set of axes, but I have to draw something here to help figure out what that angle is. Okay. Take a minute to try that. You guys online also, if you come up with it online, then in a second here, not immediately, you can chat it in for me. So find that one. It's got to have something to do with what angle. What now? It's got to have something to do with pi over 4, right? 45 degrees, correct? Right? Okay. So it's some variation on 45 degrees, right? We just have to find the right one. Okay. When I say some variation, technical way of saying that is, I know the angle that I'm looking for, its reference angle has to be pi over 4, right? Because pi over 4 is what gives me those trig ratios of square root of 2 over 2. So I'm looking for something with a reference angle of pi over 4. All right, any suggestions there? 3 pi over 4? Okay, I think that's a good suggestion. Let's think about how we arrived at that. So what I mentioned there just a moment ago is kind of ignore the sign for a moment. That minus sign is just initially just creating a complication for us. So just ignore that minus sign and look at this value square root of 2 over 2, right? You know that to have a cosine of square root of 2 over 2, you have some angle again whose reference angle is pi over 4. You might try pi over 4 itself, right? Okay, so you might first think, oh, well, the answer has got to be pi over 4. But that's not correct, right? Because if you calculate the cosine of pi over 4, what do you get? Well, you get positive square root of 2 over 2, right? So we know we're on the right track, but unfortunately here the sign turns out to be the wrong sign, right? Because we're taking the arc cosine of minus square root of 2 over 2. So we know that, again, pi over 4 is the right idea, right? but we're just sort of in the wrong quadrant, correct? So we have to find an angle in a quadrant that will give us a negative cosine. Where is cosine negative? In quadrant 3, where else, Emil? In quadrant, no, not in quadrant 4. 2 and 3, right? It's 2 and 3. Cosine is, remember, cosine, the sine of cosine comes from the sine of the x-axis. In quadrant 4, x-axis is positive, so it can't be here in quadrant. But you're right, Emil, it could be in quadrant 3, and it could also be in quadrant 2. You probably wouldn't think of the quadrant 3 possibility first, but there is an angle in quadrant 3 that is kind of a candidate here. That would be this angle. What angle is that I just drew? What now? Yeah, 225. What's that in radians, Emil? Yeah, 5 pi over 4. So you might think, probably not, but you might think, oh, I think 5 pi over 4 is the answer, because the cosine of 5 pi over 4 will be minus the square root of 2 over 2, because the reference angle for 5 pi over 4 is pi over 4, right? Notice the reference angle here. That's the reference angle. And the reference angle there is pi over 4. If you're still fuzzy about reference angles, look at the tape that I made of the test review, because it does discuss in more detail the first part of that review, which includes reference angles. Oh, let me warn you, there's a large part of that test, that the test on Wednesday, which is going to be about reference angles. So you've got to get comfortable with reference angles. Look at the problems from the sample test. Not sure what number that is, but there's a long problem there where you're asked to find a bunch of reference angles. That sort of problem is going to be on the test for sure. Okay, well, the reference angle here is pi over 4, right? So so the cosine of 5 pi over 4 will be something like square root of 2 over 2, but since we're in the third quadrant, it's going to be negative. So that seems like that could be the answer here, right? It looks like our answer could be 5 pi over 4. But Emil, why is that not the answer? So if I think the answer here is 5 pi over 4, why do I know that's wrong? Because indeed, the cosine of 5 pi over 4 is minus square root of 2 over 2. So see, I've met this criteria, right? Okay. But why can 5 pi over 4 not be the right answer? So we really should have looked in quadrant 2. Why in quadrant 3 are we? No, it's because what is the, so this is what I keep reminding you. What's the range of the inverse cosine? No, inverse cosine is 0 to pi. Yeah, inverse sine is minus pi over 2 to pi over 2. Inverse cosine is 0 to pi. But this is not between 0 and pi. That's bigger than pi, right? 5 pi over 4 is more than pi. So that is not the right answer. Not the right answer. So so we shouldn't have gone into the third quadrant. We should have used the second quadrant, right? And y'all are trying to tell me, right? What's the angle in the second quadrant that I really want here? 3 pi over 4, right? Yeah. The angle 3 pi over 4, its cosine is also minus the square root of 2 over 2, because its reference angle is also pi over 4. But this is between 0 and pi. So the right answer here is really 3 pi over. And the cosine of 3 pi over 4 is same thing, right? It's minus square root of 2 over minus square root of 2 over 2. Okay. Well, let's keep going there with some more examples. These examples at first look like they should be really easy, because notice we're composing a function and its inverse function, right? And you remember what happens when you compose a function and its inverse function? Jad answered this for me last time. What happens, Jad, when you compose a function and its inverse? Well, this is what happens, okay? When you compose a function and its inverse, that they sort of cancel each other. the two functions undo each other or cancel each other. They invert each other, in fact, and you just end up with x, okay? So f inverse of f of x would just be x. Notice that's what we have here. We have an inverse composed with the function itself. So these two things should cancel each other, and we should just get pi over 3, okay, as the result here. We'll check that in just a second, but that's what should happen here, okay? But unfortunately, you know, there's always a catch for trigonometry, right? Unfortunately, these two functions are not quite inverses of one another, right? The inverse sine function is the inverse of not the original sine function, but what? The restricted sine function. This is not the restricted sine function necessarily, okay? So these two functions are sort of inverses of one another, but not quite. So this composition you have to be careful of. It doesn't simplify quite as nicely sometimes as it should, but sometimes it works beautifully. So let's see what happens here. Do we really get pi over 3? So let's just do it. So I have sine inverse of, what's the sine of pi over 3? So there's one of your special angles. What's sine of pi over 3? 60 degrees, sine of 60 degrees. What now? Remember, sine starts at 0. Sine of 0 is 0. And then you count up, right? So what's the sine of 30 degrees? It's square root of 1 over 2, which is 1/2. Sine of 45 degrees is square root of 2. Sine of 60 degrees, this is what we're interested in, is square root of 3 over 2. All right. So sine of pi over 3, square root of 3 over 2. Now look what we're trying to find here. Sine inverse of square root of 3 over 2, that's an angle. And what do we know about that angle? Its sine has to be what? Square root of 3 over 2, correct? So what does that angle have to be? Well, what angle has sine square root of 3 over 2? We just said it, what? 60 degrees, which is pi over 3. But remember, when you're using arc cosine, the sine inverse, right? You have to get a result in the proper range, which is minus pi over 2 to pi over 2, or sine inverse. Is this in the proper range? Yeah, right. So that's it. So that's correct. Oh, so you do get pi over 3, right? Just exactly as predicted, because these functions are kind of inverses, sort of quasi-inverses of one another. But maybe that's not always going to happen. Let's try this here. So sine inverse, also known as arc sine of 2 pi over 3. So again, if we get lucky, since these functions are almost inverses of one another, right? These two should cancel, and hopefully we get 2 pi over 3. But let's see if that's really going to happen. So let's calculate this. What is the sine of 2 pi over 3? Oh, I'm gonna have to draw that one. Where's 2 pi over 3? Over here, right? In the second quadrant, 120 degrees. So this is 2 pi over 3. So what's its reference angle? 60 degrees, right? There's the reference angle, is pi over 3. So sine of 2 pi over 3 is kind of the same as the sine of pi over 3, except we've got to get the SIG in, right? The plus or minus in front correct. But in the second quadrant, what's the sign of sine? What? It's positive. Oh, okay. So we don't have to worry about putting a minus sign on there, right? So sine of 2 pi over 3 is the same as the sine of pi over 3, which is what? Just mentioned that. Square root of 3 over 2, right? So this is the inverse sine, or the arc sine of square root of 3 over 2. But I just calculated that in the prior problem. What did we get? Pi over 3, not 2 pi over 3, right? This is pi over 3. So see, this did not work out quite like we had hoped. That's the tricky thing about the inverse sine functions, or the inverse trig functions, right? They're not completely inverses of the original function. By the way, we could, right from the beginning, we could have known that this could not come out to be 2 pi over 3. Because remember, the range of the inverse sine function has to, so when you apply the inverse sine function, you have to get an angle between what? Minus pi over 2 and pi over 2, right? So you could not have got 2 pi over 3. That's too big, all right? Same thing is going to happen with the arc cosine function. So let's try this one. So arc cosine or inverse cosine of 2 pi over 3. So, you know, it'd be nice again if those two inverses canceled each other and we just get 2 pi over 3. But let's see if that's correct in this case. So let's calculate it. So what is the cosine of 2 pi over 3? So I'm going to have to think again, right? Draw 2 pi over 3. There's 2 pi over 3, right? So what's its reference angle? Yeah, pi over 3, same picture as this, right? So the reference angle is pi over 3. So cosine of 2 pi over 3 is kind of the same, well, kind of the same, right, as the cosine of pi over 3, except we just got to get the sign correct. But in the second quadrant, what's the sign of the cosine? Negative, right? So this is got to be negative, and negative how much? What is the cosine of pi over 3? It's not square root of 3 over 2. That was the sine of pi over 3. So what's the cosine? 1 over 2, right? Yeah, it's 1/2. So finally, this is what we're dealing with. Arc cosine of minus 1/2. So I have to get an angle. It's got to be between what and what? Yeah, so I've got to get an angle. It's got to be between 0 and pi, and its cosine has to be minus 1/2. Well, this is it, isn't it? Isn't it 2 pi over 3? That's between 0 and pi, right? Okay, and its cosine is, as we just laboriously calculated, right? Its cosine is minus 1/2. So indeed, the answer here is what we'd hoped for. It's 2 pi over. So in this case, it works out nicely, right? These two functions cancel each other. You can see it's not going to work out nicely in part D. Yeah, Jack. Yeah, that's right. So if you are looking at the angle and you see it's already in the proper range for the arc trig function, right? The inverse trig function, then this is going to work. So what about this one, Jad? What about arc cosine or inverse cosine of 5 pi over 3? Is that going to cancel properly? Yeah, probably not, right? Okay, because the range of the arc cosine has to be what? Yeah, and this is too big, right? Okay, that one is too big. So so something's going to happen here. What is the so let's see what happens. So what do we get out of this? So we have arc cosine of, and I got to calculate the cosine of 5 pi over 3. Where is 5 pi over 3? Is that in the fourth quadrant? That way over here? Yeah, it's way over there, right? So there's 5 pi over 3, because the reference angle is this angle, which it still is pi over 3, right? So so the cosine of 5 pi over 3, 5 pi over 3 is the same as the cosine of pi over 3, except we got to get the sign right. But not much to that, because in the fourth quadrant, what's the sign of the cosine? Yeah, it's positive. So you get ultimately what here? What does this work out to be? What's the cosine of pi over 3, we said? 1/2, right? So cosine of 5 pi over 3 is 1/2. And now we want to find the arc cosine of this, right? The arc cosine of 1/2. Remember, that's an angle whose cosine is 1/2, like 5 pi over 3. but you cannot use 5 pi over 3 because that's too big, right? You have to get an angle between 0 and pi. So what's the angle between 0 and pi, whose cosine is 1/2? What's the angle between 0 and pi that has a cosine of 1/2? Pi over 3. It's just the original pi over 3, right? Just plain old pi over 3. Don't go into the second quadrant because remember, cosine is negative in the second quadrant. So you're stuck in the first quadrant because you have to be between 0 and pi, but you can't go in the second quadrant. So you're in your best place, right? You're in the first quadrant. What angle in the first quadrant has cosine 1/2? It's pi over 3. There it is. So forgot what the answer is here, right? This is what pi over 3. This angle y has to be pi over 3, right? It's cosine of pi over 1/2. So in this case, unfortunately, the two inverse functions do not cancel each other exactly. And again, that's not because this property in general is not correct. This property is correct. It's just that the arc cosine and the original cosine function are not really quite inverses of each other. Can y'all find this one for me? So what's the inverse tangent of 1? What is the range of the inverse tangent? Remember, we discussed that. Tangent is sine over cosine. So the range of the inverse tangent is the same as the range of the sine, which is minus pi over 2 to pi over 2. So you need to find an angle for me. Remember, the result here is going to be an angle. And what do you know about that angle? Its tangent is 1. Okay. So you have to find an angle. That should be pretty easy, right? Between minus pi over 2 and pi over 2, whose tangent is 1. That's the easiest tangent of all. Okay. So what angle has that? What angle is this? So see, tangent is sine over cosine, right? So to get a tangent of 1, the sine and the cosine need to be the same. What angle has cosine the same as the sine? Pi over 4, right? Yeah, pi over 4. At pi over 4, the sine and cosine are equal, right? They're both square root of 2 over 2. Okay, so this looks like it's got to be what? Pi over 4? That's in the proper range, correct? Because the range of the inverse tangent function is minus pi over 2 to pi over 2. So pi over 4 definitely falls in that range. What about inverse tangent of square root of 3? This one is one it's good to experiment a little bit with. Okay. All right. Just again, you're looking for an angle whose tangent is square root of 3. So try experimenting with some of your special angles and see if you can find one whose tangent is square root of 3. Because, and the way you experiment is remember that tangent is sine over cosine, right? So let's try a few. What about tangent of pi over 6, which is 30 degrees? Remember, that is sine of 30 degrees over cosine of 30 degrees. What's the sine of 30 degrees? Sine of 30 degrees, what? No. It's 1/2. All right, keep telling y'all how to remember this. I'll keep learning. What sine of 0? 0. Sine of 0 is 0. And then remember, you count up in the numerator and take the square root and divide by 2. So just run through your special angles. So 30 degrees, sine of 30 degrees is square root of 1 over 2. That's 1/2. So that's already it. For 45 degrees, it's square root of 2 over 2. For 60 degrees, it's square root of 3 over 2. Up to 90 degrees, square root of 4 over 2. Square root of 4 is 2, so you have 2 over 2, which is 1. So sine of 90 degrees is 1. All right, so the sine of pi over 6 is 1/2, but the cosine is square root of 3 over 2. And that's not square root of 3, right? If you reduce that, you don't get square root of 3. Actually, what you get is 1 over the square root of 3. Oh, close, right? So we wanted square root of 3, but we got 1 over the square root of 3. Let's try another special angle. Not 45 degrees, because what's the tangent of 45 degrees? 1, right? Okay, so we don't have many choices here. Let's try pi over 3, right? So what's the sine of pi over 3? That's square root of 3 over 2, right? What's the cosine of 1/2? And so what's that give us here? Did I do this one right? Then was I calculating cosines right a moment ago? Oh, I was. Okay. So what does that reduce to? Well, the halves divide out and you get square root of 3. So that's what you're looking for. It's pi over 3. So our answer here has to be pi over 3 because the tangent of pi over 3 is square root of 3. Is this in the proper range? Remember, the range for the tangent is minus pi over 2 to pi over 2. So that certainly is in the proper range. So that's got to be the right. That's got to be the right answer. Let's test that with your calculator. So you can punch in square root of 3 on your calculator. It's about 1.7 something. But your calculator will calculate it exactly. And then compute the arctangent of that with your calculator, which is probably the shift of the tangent key on your calculator or something like that. Let me see if I can do this. The square root of 3 is about 1.73. It's 7 or lots of decimal places. And then the inverse tangent of that, which on my calculator is the shift of the tangent. I'm in degree mode, and it comes out as 60 degrees. That's it, right? Okay. That is pi over 3. If you're in radian mode on your calculator, you're going to get a little bit more than 1, which is pi over 3. Okay. All right, we're going to look at some applications here of inverse trig functions. And these applications, to start with, are really straightforward. So we're back to solving triangles again, okay? And but now, instead of looking for the length of a side of the triangle, we're going to be looking for the size of an angle in the triangle, right? Which we should also be able to do if we're given the right information. Okay, so let's pause there momentarily. So we'll take a break before we come back and look at this one. Y'all can play with it in the break if you want to. So I'm going to pause the recording, and then we'll resume here in about 10 minutes. With a very easy, but this is an important example because this really demonstrates how inverse trig functions are used in practice, but in kind of a simplified example. So we just want to solve this triangle. Well, actually, we just want to find this angle in the triangle, right? So we're not really asked for this side, the length of this side, but eventually we can find that, right? But namely, we just want to find the size of this angle theta in this triangle, which has this hypotenuse of 50, right? And then this opposite side length is 10. So to find theta, right, you're going to have to set up an equation involving theta. That's always the way you find unknowns, right? And this equation is going to involve a trig ratio, right? We're going to set up a trig ratio involving theta, correct? So let's look and see which trig ratio would apply here. For theta, we know the opposite side, right? And we know the hypotenuse. So it looks like we would use what? What, Hannah? No, not the Pythagorean theorem, right? Because in the Pythagorean theorem, we would have to know, we could use the Pythagorean theorem to find the length of this side, but we're not looking for the length of this side. We're looking for the size of this angle. So what I'm asking is, what trig ratio could we set up involving theta using the information that we do know, Hannah? Sine, right? Because we know the opposite and we know the hypotenuse, correct? Okay. Or you could use the cosecant if you wanted to, okay, all right, because that also involves the opposite of the hypotenuse. But more likely you're going to use sine, right? So let's write down that equation. We would have sine, right, of theta is equal to, well, what's it equal to in this triangle? What, 10 over 50, right? Which I guess we can reduce to 1/5 if we want to. And we want to solve this equation for theta. But notice now that the theta is trapped inside the sine, right? See, we want to solve for theta, but theta here is trapped behind the sine. So we need to get rid of the sine. You cannot divide out sine. Sine is not a product there. Sine is a function, correct? So how do you undo or cancel that sine function? So what mechanism allows you to cancel functions? Your what now? No, we cannot move the sine to the other side. That would be kind of like dividing by sine. But this is not sine times theta. This is sine of theta. Sine is a function, right? So how do we undo functions? What's the trick that we've learned for undoing functions? What? Inverses, right? See, inverse functions are what allow us to undo functions. Okay, so what I'm going to do here is apply the inverse to both sides, keeping in mind, of course, that this inverse is not quite the inverse of the original sine function, right? But it's the best I can do, and we can always, you know, adjust our answers at the end if we have to, right? Based on what we know about the arc sine function. So make sure you apply the arc sine or the sine inverse to both sides, right? You got to do it to both sides because this is an equation. And then hopefully what happens here on the left-hand side, what? They cancel. And so you just get theta, see, right? Just exactly what you're looking for. Now, remember, we do have to be careful, right? That because sometimes, as we learned in those prior examples, right? When you compose sine inverse with sine, they don't cancel each other perfectly. But in this case, theta is an acute angle. It's between 0 and 90 degrees. So I'm guaranteed, because theta is just an acute angle between 0 and 90 degrees, I'm guaranteed that this cancellation is going to work fine. All right. So, so indeed, arc sine of theta will become theta. And now we just have to calculate what is the arc sine, the sine inverse of 1/5. That's where your calculator is going to have to help you, okay? Because I don't know any angle whose sine is 1/5, but the calculator does, right? We're not going to get a special angle, all right? This would have to be 1/2 or square root of 3/2, something like that, right? To have a special angle, but no special angle gives you a sine of 1/5. So you just use your calculator and compute arc sine of 1/5. What does the calculator say? This doesn't say degrees or radians, so I guess you can give me either one. Is fine there, right? 11.5? Yeah, about 11.5, right? Okay. So actually, if we round off to a couple of decimal places, it's 11.54. This is in degrees. All right. So there it is in the picture, right? The theta is 11.54 degrees. See, now we can in solving right triangles, we don't just have to solve for lengths of sides, right? But we can also now solve for angles as well by using our inverse trig function knowledge. I'm going to let y'all try one. This is equally easy, although it's in a stated problem, but it's really just a right triangle. So we have a 40-foot ladder is leaning against the building like this, right? And the base of the ladder is 6 feet from the building. I wonder if that's safe. But anyway, it's 6 feet from the building. What is the angle formed by the ladder and the building? Okay, so what is this angle? So can y'all solve that one? So you're going to set up an equation, right? And you'll need your calculator. Make sure you write down the equation and try to write down the steps like we did in the previous example. We wrote down the previous example. I can't scroll back up and show them simultaneously, but so that just so you'll have clear in your mind what the steps are. You can, this one is so easy, you could probably do it just almost by thought, but try to write down the steps. So you guys at home also, right? What is theta in that picture? What's this angle between the ladder and the building, right? Okay. This picture. Yes. You know, often in the state problems, they will give you different frequency. That's it, my practice. But in your homework, as always, be careful. But it's that's what. Yeah. So. So that at least when back to that was good. So, one more time, so. So. So, okay. Sorry. Sorry. So, actually, right. So, sorry. Fine. That's fine. Sine. Like sine. Okay, let's write down. So, yeah. Sine. Sides. Right. That one. Here. And you calculate. Good. Okay. Did someone get the answer at home there? Did y'all come up with a number? Yeah, Ken, I think that's right. So let's see how we arrived at that. So I think everyone wrote down the equation nicely. We know theta, we know sine of theta, I'm sorry, sine of theta is equal to opposite there over hypotenuse, right? So that's 6/40, which if you want to, you can reduce that to 3/20. So, but now we have to solve for theta, right? So we have to eliminate the sine. Yeah, and since sine is a function, the way you can undo the function or eliminate the function is by applying its inverse, right? So you take sine inverse. This is what's great about inverse functions. They help us solve equations like this one. So we have sine inverse of sine of theta is sine inverse of 3/20. And now these should cancel each other, right? And they're going to here for sure, right? You won't have any complications here because again, theta is just an acute angle. So you're not going to have this issue of possibly coming out with the wrong. And now we just have to calculate what is, according to your calculator, the inverse of the sine inverse of 3/20. And it's something like what, 8.63? Yeah, in degrees, it's about 8.63. Okay. Yeah, in a practical application like this one, you probably give the answer in degrees, right? That would make more sense than giving it in. That's easier to understand than giving it in radians. Let me show you one more example, but this is not one where we're going to come up with a numerical example, a numerical answer. I mean, this says a lighthouse is located on. I'm sorry, a lighthouse is located on an island that is 2 miles straight off of a shoreline. So scroll up a little bit. Here's the picture. Oh, I see. So there's the 2 miles. So the lighthouse is 2 miles, I guess, due whatever direction that is west, right, of this shoreline. Okay. And what are we doing with that? Express the angle formed by the beam of light from the lighthouse, okay, and the shoreline. So that angle between the beam of light and the shoreline as a function of this distance d given in the picture. All right, so here's what they're asking you to do. Okay, so you got the lighthouse, right, and of course it's shining a light, and as you go a certain distance, say north of this due east-west line, right, from the lighthouse to the shoreline, of course the light shines that far because this is a lighthouse. But the further you go up, this angle between the beam of light and the shoreline is going to change, right? Okay. If you're standing, say, way down here, maybe right there, then that angle is going to be rather large, right? This angle formed is going to be kind of large, almost 90 degrees, right? Okay. But as you go further up, then the further up you go on the shoreline, the smaller this angle becomes, right? Okay. This angle between the beam of light and the shoreline. If you were to move way up here, right, along the shoreline, then the angle would be even smaller. So at different distances, you get different angles in this right triangle, correct? Now, they're not asking you, they're not giving you this specific distance and asking you to compute the size of angle. What they want you to do is write down a formula that you can use to compute the size of this angle based on any distance that's given, all right? So can we come up with a formula, in other words, a function, right, based on this distance that we step north here, okay, that would give us the size of the, angle at that particular distance. So, what I'm asked for is exactly what's expressed in this equation, right? Can I find a formula involving this variable d so that if I change d, right, I can compute this angle for different values of d. Well, let me show you how you can think about this. All right, so just looking at the picture that we're given, right? Okay, here's theta, and we know this distance is 2 miles, and this length we're calling d. So even though we're not giving it a specific numerical value, we're giving it a name d. So what trig ratio here can you form with theta based on this information? You know this distance, and you have a name for this length. Is that tangent? Yeah, tangent would work, right? Y tangent adjacent, correct, right? So the opposite of theta here is always what? No matter how far you go up the shoreline, what's the opposite of theta? 2, right? It's this length, correct? Over, and then what's the adjacent side? Well, that's going to be a d, depending on how big this distance is, right? So we don't have a specific value for d, but we have a variable name for that length. It's d. So we know that tangent of theta is going to be 2 over whatever this distance d is, right? Now, I want to solve this equation for theta, right? Because see, if I solve this equation for theta, then I'll have a formula for theta, correct? So how do I solve this equation for theta? Inverse what? Sure, right. Just apply the inverse tangent, right? To both sides. And these two should cancel each other, correct? And in this case, they'll cancel each other properly because, again, theta is just an acute angle, right? It's between 0 and 90 degrees. So I know that this cancellation will work without any difficulty. So there it is. There's my formula. Theta is the inverse tangent of 2 over d. So if you're given a value for d, if you're given a value for this distance, just plug that into this formula, take 2 divided by d, and then use your calculator to get the inverse tangent, and there you'll have theta, right? Okay. So when you're asked to write down some quantity as a function of another, that means you want to write down a formula that will give you that quantity. You want that formula based on the quantity that's given. Okay, so we wanted to write down a formula for theta based on value. Well, there's our formula. It's not an algebraic formula; it's a trigonometric formula, right? But still, it's a formula. Okay. Well, let's continue in sort of this spirit of solving equations. So I'm going to skip to the next notes here, and we just have a bunch of equations. that we want to solve. And they're pretty straightforward. So they're not actually that difficult to solve the equation, but the issue comes in with what we mean by solving an equation in an abstract equation like this one, where we don't know how we're using theta in practice, right? Okay, so well, let's start here. So I have sine of theta is equal to 1/2. So you can almost solve that by inspection, right? You're looking for an angle whose sine is 1/2. You can just almost guess now what the answer is there, right? Okay, without going through a lot of steps, but still, let's go through the formal steps. So to solve this equation for theta, right, I have to get theta equal something. So I have to get rid of the sine. How do I get rid of the sine there? What? Yeah, you apply sine inverse, right? So I have sine inverse of sine of theta is sine inverse of 1/2. In other words, there's my answer, right? Theta is sine inverse of 1/2. So I need an angle here whose sine is 1/2. Well, you can write down one value for theta for me pretty easily. What's an angle whose sine is 1/2? Just starting the first quadrant there. What? 30 degrees, right? Yeah. Okay. Yeah, that's the first one, right? Okay, which is pi over 6. So we know that theta here, at least one solution to this equation is pi over 6. Okay, because the sine of pi over 6 is 1/2, right? Now, but here's the issue that comes up when you're solving equations. Normally, when you're told to solve an equation, that means you want to find all possible solutions to the equation. Okay? All possible solutions to the equation. So pi over 6 is indeed a solution to this equation, but there are lots of other solutions as well. And we want to see if we can write them down. Okay, so that's where solving trigonometric equations like this one becomes tricky. It's not always finding just one solution, it's trying to write down all the solutions. So you already told me that pi over 6, that's a little bit too big, right? But close enough. So you already told me that one solution here for theta is pi over 6. That's correct. All right, but let me show you. You can create lots of other solutions, because if you take pi over 6 and you add in one full revolution, so pi over 6 plus one full revolution, so that angle would look like this. I'm sorry, I drew it wrong. So pi over 6 plus one full revolution, that also is going to be a solution to this equation. What is this angle? Oh, well, it's pi over 6 plus one full revolution. So altogether, how much would that be? That's 13 pi over 6. So another solution to this equation is 13 pi over 6. See, okay, pi over 6 plus one full revolution. And guess what? You can keep doing this. So if you added on another revolution, you would still get a solution to this equation. Wow, what's another revolution added on here? What is that? 25 pi over 6? Yeah, right. And obviously you can keep doing this indefinitely, just adding revolutions, right? And you'll still get solution to the equation. So you get, notice that, so this equation becomes complicated really quickly. You actually have infinitely many solutions to this equation already, all right? Because just take the pi over 6 and keep adding multiples of 2 pi. Just add 2 pi, another 2 pi, another 2 pi. Actually, you can also subtract multiples of 2 pi, okay? And so instead of adding 2 pi, you could also subtract one revolution. And you'd still get a solution to the equation, okay? Whew, that's a lot. So here's how we can express all of those solutions kind of quickly. So start with the basic solution of pi over 6. And then just write this. I can add or subtract, right, any multiple of 2 pi. So k here represents a multiple of 2 pi that I'm adding or subtracting. And so k can be 0. 0, I just get pi over 6. Or k can be 1. That would be pi over 6 plus or minus 2 pi. Or k can be 2. That would be pi over 6 plus or minus 4 pi, etc. So pi over 6, usually you don't have to write this part down. It's kind of understood. Just pi over 6 plus any multiple of, or minus any multiple of 2 pi. However, guess what? That's not all of the solutions, okay? All right, that's not all of the solutions. There's another set of solutions also to this equation. We can still find them now pretty easily, though. Let me show you how to look. Again, you want to find an angle whose sine is 1/2, right? You want to find an angle whose sine is 1/2, okay? Is there another angle from 0 to 2 pi? It's got to be between 0 and 2 pi. Is there another angle whose sine is 1/2? But don't use, yeah, it's got to be between 0 and 2 pi, okay? So it's got to, it's reference, it cannot be, it's got to be different from pi over 6 plus a multiple of 2 pi, okay? So is there another angle minus 11 pi over 6? No, that is pi over 6 minus 2 pi, okay? So that's really pi over 6 again. But Fernando, what's another angle whose sine, between 0 and 2 pi, whose sine is going to be 1/2? So this is positive. So where is sine positive? First and second quadrant, right? Okay. So in particular, in the second quadrant, right? So is there an angle in the second quadrant whose sine is 1/2? Isn't it this angle right here? Yeah, 5 pi over 6, because the reference angle is pi over 6. That is another possibility here that we have to list. It's separate from pi over 6 plus or minus a multiple of 2 pi. If you take pi over 6, the original solution here, and you add or subtract 2 pi, you're always going to end up in the first quadrant. Won't end up with this angle in the second quadrant. So you have another possible solution here, 5 pi over 6. And then again, you can add or subtract multiples of 2 pi. All of those numbers will also be solutions to that equation. Wow, there's a lot. Okay, see all of those? All right. So pi over 6 plus or minus any multiple of 2 pi, and then 5 pi over 6 plus or minus any multiple of 2 pi. So lots and lots of solutions. All right, let me show you what we did there, okay? So to solve this equation, start by finding what are called the basic solutions to the equation, all right? That is two solutions that give you a sine 1/2, and they have to be between 0 and 2 pi. So find two solutions between 0 and 2 pi. And then they have to be separate though, all right? And then just add multiples of 2 pi. That's how you get all the solutions. That's the basic strategy. So find two basic solutions, that is two solutions between 0 and 2 pi, and then add multiples of 2 pi. All right, let's try that one. Let's try that again, because this is going to take some practice. This is a tedious process. All right, so let's look at solving this equation, which seems like it should be so straightforward, right? Cosine of theta is square root of 2 over 2. So you know immediately, right, that that theta has to involve what? Pi over 4, right? You can find that, by the way, just by applying the inverse cosine to both sides. And when you do that, you get that theta is pi over 4. So one of your, because the cosine of pi over 4 is square root of 2 over 2. So one of your basic solutions is pi over 4. That's a solution between 0 and 2 pi, because cosine of pi over 4 is square root of 2 over 2. Now, how do you generate new solutions from this basic solution? What do? Add or subtract multiples of what? 2 pi. So pi over 4 plus 2 pi, that gives you another solution. Pi over 4 plus 4 pi, pi over 4 plus 6 pi, or you can also subtract. Pi over 4 minus 2 pi, pi over 4 minus 4 pi, etc. Get all of these thousands of solutions, but they all have this pattern. But that's only one of our so-called basic solutions. One of the solutions between 0 and 2 pi. We need to find another one, because you have to find two. If you can find two, that will generate all of them, I promise, okay? So what's the second one? It's not 3 pi over 4, Emil, because unfortunately 3 pi over 4 is over here, and the cosine of 3 pi over 4 is negative, because cosine is negative second quadrant, right? What now? Yeah, so see, this cosine is supposed to be positive square root of 2 over 2, right? So you can't be here. Where'd y'all tell me? Yeah, over here, right? Okay, at 7 pi over 4. Because you're in the fourth quadrant, cosine is positive, and the reference angle is pi over 4. So the cosine of 7 pi over 4 is square root of 2 over 2. Remember, you have to get two solutions, two basic solutions. They have to be between 0 and 2 pi. So this fits the bill. Don't use minus pi over 4, okay? Although that would probably work as well. All right. Use 7 pi over 4. So what else can theta be here? 7 pi over 4, and then what? Plus or minus some multiple of that. By the way, minus pi over 4 is a solution to the equation. Where does that come in this list? Minus pi over 4, its cosine is positive square root of 2 over 2. So that's a solution to the equation. But how does that come out of this list of, because this is supposed to be all the solutions. Isn't that's 7 pi over 4 minus 2 pi, isn't it? Yeah. Take 7 pi over 4 minus 1 times 2 pi, you get minus pi over 4. So minus pi over 4 is in this possible list of solutions. That should be all the possible solutions. Yeah, Jen. No, yeah, that's inverse cosine. It's supposed to be between 0 and pi. So when I applied inverse cosine, I did, well, I didn't show it there, but we do get here pi over 4. That was our first basic solution. Okay. But in solving this equation, notice this original equation, Jad, doesn't involve inverse cosine, right? You're just supposed to write down any angle of any size whose cosine is square root of 2/2. So you get lots more possibilities than just this one. Yeah. Oh boy, let's try another one. All right, so cosine of x is 1/2 or minus 1/2, right? So you can start if you want to by using inverse cosine, that's fine, but that's only going to get you like halfway there, right? So we should get x equals to inverse cosine of minus 1/2. What is that going to be? So see, you have negative cosine, right? So you have to be in what quadrant there? Yeah, second or third, right? Cosine is negative in the second or third quadrant. But Jad, now Jad, this is where your observation applies. If I write down inverse cosine of minus 1/2, I want to be in what quadrant? Between 0 and pi, but this is negative, so which quadrant? Yeah, not 3 though, because you told me that if I compute inverse cosine, I have to get an angle between 0 and pi. 2, yeah. So I know I'm in quadrant 2. Y'all see what we're complaining about here? Inverse cosine of minus 1/2. Since cosine is negative, I've got to be in the second or the third quadrant. But inverse cosine only gives you an angle between 0 and pi. So you can't be in the third quadrant because that's bigger than pi. So you've got to be in the second quadrant to write down solution to that expression. So that's in the second quadrant. So where in the second quadrant do I have cosine 1/2? What angle has cosine 1/2? What? Yeah, the reference angle is pi over 3, right? So you would be at 2 pi over 3, correct? Because the reference angle has to be pi over 3 because cosine of pi over 3 is 1/2, right? But we want an angle in the second quadrant, so that would be 2 pi over 3. Oh, so this is so x here is 2 pi over 3. Oh, great. So we've got one solution. We've got one solution. So we're in good shape. What do I do with this solution to generate more solutions? Yeah, multiple of 2 pi. So add or subtract any multiple of 2 pi. That will give you another solution. In other words, just go one revolution from 2 pi over 3, either in the positive or the negative direction. You'll get another solution to this equation. Unfortunately, that's a lot of solutions, but that's not enough. That's not all of them. Okay, so now we have to figure out where the rest of them are. All right, now you have, this is where you really have to use your knowledge of trig, right? So I still need an angle whose cosine is minus 1/2, but it cannot be this one, right? So the arc cosine is not going to help you. You're just going to have to imagine what that other angle is. So what's another angle whose cosine is minus 1/2? It can't be in the second quadrant because I've used this one. So where is it? Yeah, it's in the third quadrant, right? It's over here in the third quadrant. And what angle is that, Fernando? Just what? What'd you say? Yeah, that's 4 pi over 3, right? Is it 4? Yeah, 4 pi over 3. I drew it too big, didn't I? Anyway, it's over here at 4 pi. 4 pi over. Because the reference angle is still pi over 3. But since we're in the third quadrant, the cosine is going to be negative. So our second basic solution is 4 pi over. And then just add or subtract a multiple of 2 pi to that. So there's your full collection of solutions. You're going to have to type in something very similar to this in WebAssign, okay, when they ask you to solve these equations. But I forgot what to do with the plus or minus. So, because you can't, there is no plus minus, I think, in the WebAssign palette, okay? Put what now? No, both of, yeah, you have to put both of these lists. And I'm not sure how to get how to indicate the fact that you may just have to put plus here instead of both plus or minus. If the k is negative, then you don't need to allow k to be negative. You don't need minus. Okay, I'm gonna let y'all try this one. All right, so this is going to be a special angle, square root of 3 over 2, right? So remember, what you want to do is you want to find two solutions between 0 and 2 pi, two different solutions between 0 and 2 pi. One of them you can find by using arc sine. So you can use sine inverse to solve this equation. But the second one you're going to have to find just by inspection. So see if you can find two solutions between 0 and 2 pi to that equation, and then you just add or subtract multiples of 2 pi from those two solutions, and that gives you every possible solution. This one is kind of trickier because this one involves a calculator, but this one is a special angle. All right. So first, just find one answer to the question. You can do that by applying the inverse sine to both sides. That would allow you to get one list of solutions, but the second list of solutions you're going to have to think about more carefully. All right. So you guys at home also see if you can write down all the solutions to this equation. But start just by getting one. Minus, but it's just square root. That's a special. Sine is positive. So, sine. Sine. Here's sine. Okay. So So you can either make it. Yeah, that's sooner. Just that's the second. All right. This is a good one. Yeah. They're in the wrong one. Oh, we're running out of time, folks. Yes, I'll find something here. Yeah. Well, sine is always a negative. That's why. So it's going to be second or fourth. Second or other. Yeah. Second one, so sine has to be. All right. Okay. So let's finish this one for you guys at home. Let me show you all this one. Most people are doing it really very well. Y'all did that very well because this is very confusing, I think. So to solve this equation with using sine inverse, you would have to go to a negative angle because remember, the range of the sine inverse function is minus pi over 2 to pi over 2. So you need an angle in the fourth quadrant to get a negative sign. And that would be like this, minus pi over 3. Remember, for arc sine, you need an angle between minus pi over 2 and pi over 2. So this answer is minus pi over 3. So there's one of your solutions, minus pi over 3. And then just add on again or subtract any multiple of 2 pi. Some of y'all wrote this as instead of minus pi over 3 as positive 5 pi over 3, which would bring you to the same place. That's fine. That's fine. Now, where's the other angle though? Right? Whose sine is? It's got to be in the third quadrant, right? Because that's the only other place where sine is negative. So it's this angle. It's got to have also reference angle pi over 3. And this angle, if you write it as a positive angle, that is 4 pi over 3. But you could have also written it as minus 2 pi over 3, and that would have worked. So the other list of solutions there is 4 pi over 3, right? 4 pi over 3 plus or minus a multiple of 2 pi, or you could have written minus 2 pi over 3 plus or minus a multiple of 2 pi. Okay, all right, so so if y'all can read that, there are the solutions to all the solutions to this equation. This one's a little bit harder, so we'll try this one maybe as a review after the test, because notice 0.65, there's no special angle that gives you cosine of 0.65. So we're really going to have to rely on our calculator here to help us. And this gets then very messy to write down all the solutions. Okay, but we can work through it. But you really do need to scribble a picture in that case. All right, so we're out of time. So test Wednesday, you guys show up at the right time. Make sure you've got your survival card and make sure you prepared, right? So I'll see you guys on Wednesday. Are there questions? Yeah. It's starting with the trig through composition and inverses. So look at the sample test and you'll see what the material is. No, next time. No. Yeah, Wednesday. Yeah, next time I see you is test. M. Yes. Yeah, what's your last name? Sanchez. Yeah, so you will come at 11:50.